Hello, everybody. Thank you very much for joining this talk. My name is Gal Loren, and this is a joint work with Professor Leonid Berenbaum. Today, I would like to talk about some last result we achieved in my research on backup placement, specifically about backup placement in WSNs in the network management distributed setting. My talk will be divided to 3 consecutive contents. We will start with some intro to the topic, including previous results. Then we will move to define the problem in the new setting of distributed network management. Finally, we will present our new approach to solve this problem using an adaptive clustering refinement, which actually managed to achieve more than just good backup placement. Let's start with some intro. First, we formalize the dynamic network management setting configuration. In this configuration, computation proceeds in synchronous rounds, and all IDs are distinct. Each round in a distributed algorithm consists of 3 stages. 1, each node in parallel to other nodes receives messages sent by its neighbors at the previous round. 2, each node in parallel to other nodes performs a computation. 3, each node in parallel sends messages to its neighbors. The dynamic network management setting is based on the congest setting, with the following additional features. Each vertex has a cost that accumulates during the round of execution. In each round, each vertex V may add edges to a certain distance k in G. A vertex may also remove edges that connect it with vertices outside of its immediate neighborhood. Increasing the transmission range by a distance r increases the transmission cost by a function fr. For example, fr is quadratic in the plane and cubic in the 3-dimensional space. Analogously, decreasing the transmission range by r decreases the cost of a vertex by fr. Such a definition of cost may be proportional to energy consumption in wireless networks when an appropriate function fr is used. So we finally reached to the backup placement problem. This problem was introduced by Halderson, Kohler, Pachamira, and Rabitz in 2015. In terms of graph theory, the problem in its simplest form is defined for a network graph GVE as follows. Each vertex V in V is selecting a neighbor such that the maximum number of vertices in V that select the same vertex is minimized. The problem is well motivated by computer networks whose nodes may have memory faults and wish to store backup copies of their data at neighboring nodes. But neighboring nodes may incur faults or be overflowed as well. And so the number of nodes that select the same backup node should be minimized. This way, if a backup node incurs faults, the number of nodes in the network that lose data is minimized. Put theory aside, why this problem is so important for real life and actual problems. So the possibilities of an absent node, damaged communication link, or missing data are unavoidable in wireless networks for many causes, environmental and internal alike. As today IoT networks grows in scale and there is a need for high rate sampling, the problem gets even worse since those requirements are mostly dependent on the hardware and the wireless setting. Moreover, a proper backup placement allows each vertex to perform a backup to a neighboring node rather than a more distant destination, and thus improves network performance. In addition, nodes' memories are used to the minimum extent for the purpose of backups, which makes it possible to maximize the memory available for other purposes of the vertices. Let's take a look on some basic examples. On the middle, you can see a cycle graph. The optimal backup placement solution would be if each node selects its succeeding neighbor to be its backup node. And by that, the maximal backup burden for each node will be of only 1 unit, a good result. On the left, you can see a star graph. The optimal solution will force all the nodes to choose the center node, beside the center node itself, to be its backup node. And by that, the maximal backup burden would be of the size of V minus 1, a less good result. On the right, you can see a rooted unoriented tree. The optimal solution in this case forces all the nodes to choose their parents besides the root to be their backup nodes. By that, the maximal load is delta. So after we got familiar with the problem and the new setting, let's see why we need to redefine the problem given those settings and how this change the setting can be helpful. When we consider reality, we can understand the problem in a much fine-grained manner and ask the question less formally by how exactly to transfer the data outside of the loaded area dynamically to a less overloaded area. How to do so in a distributed fashion. how to guarantee this process will work in any network condition, and most importantly, how to do so fast and best. Given a real network such as a WSN or software-defined network, we clearly understand that the strict congest settings are not optimally described in reality, as the network structure can change, and this can cause tremendous impact to current backup placement algorithms, including performance degradation. Until recently, Halderson and Al algorithm remained the state-of-the-art for general graphs, as well as for specific graph topologies. Very recently, this was improved by Langley, Bernstein, and Sadi, who devised an algorithm with O1 approximate backup placement for general graphs. Bourbon and Oren obtained significantly improved algorithms for specific graph topologies. Specifically, they showed that O1 approximation to optimal backup placement can be computed deterministically in O1 rounds. In wireless networks, certain social networks, Clophy graphs, and more generally in any graph with neighborhood independence bounded by a constant. At the other end, they considered sparse graphs such as trees, forests, planar graphs, and graphs of constant arboricity, and obtained constant approximation to optimal backup placement in O log n deterministic rounds. Barber and Oren also devised an additional algorithm for dense graph topologies, including unit-disk graph, unit ball graph, line graphs, graphs with bounded diversity, and many more. This algorithm requires just one round and consists of just a single, very simple operation. Surprisingly, such a simple one-round strategy turned out to be very efficient for backup placement computation in dense networks. Not only that it improved the number of rounds of the solution, but also the approximation ratio is improved by a multiplicative factor of at least 2. Previous results are less efficient as the bounded independence could be relatively large and the performance degradation will occur. Thus, in set setting, it is suitable to form low degree trees, which interconnect the different active parts of the entire network in order to achieve good performances. This makes it possible to obtain a balanced backup placement while optimizing connectivity, energy, memory, and storage space. To this end, we redefine the problem in terms of WSNs as follows. We are given WSN consisting of a two-dimensional array of n nodes, each of which is marked either as a base station, a cluster head, or a non-cluster head, that are placed on a squared root n grid. The goal is to find a backup placement for data packages that minimizes the maximum load on a node, i.e., the number of nodes that perform backup to the same destination. Our approach toward the solution relies on the reconfigurable nature of the whole network, which eventually would be able to balance the load in an overloaded network properly and accomplish a proper backup placement. We investigate whether hierarchical WSN can benefit from a distributed constant refinement of the network structure based on the idea that a load balanced network would be more energetically optimized. Unlike other WSNs clustering algorithms that do not recluster the network after deployment, our hypothesis is that it is advisable in terms of prolonging the network lifetime to adaptively recluster specific regions that are triggered significantly more than other regions in the network. While we consider sensors as triggered if it's been activated by external events to perform sensing, processing, and transmission actions. By doing so, it is possible to minimize or even prevent the premature death of cluster heads, which are heavily burdened with sensing and transmission actions, much more than other parts of the WSN. Long story short, by using our dynamic tree structure called an ACR tree, we obtain an overall energy cost of O n log n. This improves upon a straightforward approach when all vertices communicate directly to the root. In such case, the overall energy consumption is theta n squared, which is significantly larger than the ACR tree 1. This ACR tree immediately gives rise to basic backup placement, as each vertex can send its backup to its parent and the root to one of its children. Specifically, a backup placement of load of at most O1 can be maintained within O log squared n update time and an O n log squared n energy consumption. Let's see how this ACR tree works. The first problem we are focused on is the ACR tree problem. ACR trees make it possible to efficiently gather data from the triggered vertices into the destination node, which is the root of the tree. The ACR tree T must fulfill the following goals in the end of each step. 1. All trigger vertices have a path to the root of T. 2. The number of children of each vertex in the tree T is bounded by a constant C. 3. The height of the tree is bounded in the following way. Let's n hat denote the number of triggered vertices. The height of the tree is bounded by O log n hat. Note that n hat may be significantly smaller than n in some steps. In view of the above mentioned considerations, an ACR tree has several advantages. It makes it possible to improve energy consumption while bounding the load on parents, which originates from their children. In addition, information propagates quickly to the root thanks to the bounded height of the tree. This is in sharp contrast to certain extreme scenarios, such as connecting all nodes directly to the root, which causes excessive power consumption and load, or on mainlining a fixed tree of depth log n all the time, which may be much higher than needed, which causes slowdown in information aggregation by the root. Now let's see how the algorithm makes decisions based on local behavior of clusters rather than taking into account the global behavior of the entire network. In this way, we can obtain efficient update time of our algorithm without compromising energy efficiency significantly. The algorithm is executed by all vertices V and V in parallel. The main idea of the algorithm is the following one. Once an energy use of a cluster becomes higher than a certain threshold, we partition the cluster into C subclusters, i.e., into C quadrants whose size is smaller by a factor of C. The cluster partition is performed in the number of if the number of triggered vertices in the cluster is greater than C. This results in adding new cluster head nodes to the ACR tree as leaves that become the children of former leaves from a previous step. These new leaves correspond to the newly formed clusters. Then this process is repeated recursively by checking in parallel whether each of the new smaller clusters has more than C triggered vertices. This refinement results in a better energy use in each such newly formed cluster, since the transmission diameter becomes smaller. In other words, we balance cluster of excess energy use by decomposing them into smaller clusters that requires less energy. An opposite operation in which some clusters are merged into larger ones may also be required. This happened when several clusters have less than C triggered vertices altogether and can be merged. This is performed using the ACR tree as follows. Each vertex in the tree whose all children are leaves checks how many triggered vertices there are in clusters of these leaves. If the number of such triggered vertices is at most C, then these clusters are merged into a single one and the leaves are removed from the ACR tree. The parents of the leaves become the cluster head of the new cluster. Then this process is repeated recursively. Consequently, the energy use of vertices in the newly formed larger clusters may grow, but the tree distance between the root to some leaves decreases. Our algorithm employs a subroutine for determining how many triggered vertices there are in a cluster without requiring transmission between all these vertices and the cluster head. This can preserve a significant amount of energy. For example, in the initial step, the root is the only vertex in the ACR tree, and we would like to avoid the situation that numerous triggered vertices have to communicate directly with the root in order for it to learn how many such vertices there are. Instead, this information is going to be acquired using a much more energy efficient subroutine. And that's about it. Let's see an example. In this one, we can see the formation of an ACR tree. The root node in blue is associated with an entire vertex set V, and it is in the center of the plane, which is partitioned into quadrants recursively, only in one out of the 4 quadrants in this case, 4 times while C equals 4, resulting in a tree of 16 cluster heads. Now, that is a pretty simple example. Let's imagine this process in different regions of the networks, in refinement and coarsening simultaneously, on and off constantly. In order to prove that the algorithm works as we think, we prove the following theorems. We learn from those theorems that the maximum energy consumption in the ACR tree is n log n. We know that in case where the tree is not used, an extreme scenario is when all vertices communicate directly to the root. In such case, the overall energy consumption is theta n squared, which is significantly larger than the ACR tree one. The above presented ACR tree immediately gives rise to a basic backup placement, as each vertex can send its backup to its parent and the root to one of its children. In the network management setting of a grid, a backup placement of load at most C+1 equals 5 can be maintained within log squared n update time and an ON log squared n energy consumption. Thanks for listening.